All right. So this week we were talking about taking derivatives algebraically. We learned a lot of different rules for approaching how to take some derivatives. So that's kind of what we're going to be doing today. I usually just play this out as we're going to be doing a lot of practice problems, because the best way to learn these rules, in my opinion, is to use them. So yeah, did anyone have any questions about what we did this week? We did the power rule in section 3.1. We did exponentials and logs in 3.2, and then 3.5 is periodic functions, generally speaking. So there's no direct questions. We can just start doing a couple problems. All right, let's start in 3.1. This one we're working a little bit with the power rule. I'm on page 143. And let's do question let's do 6, and let's do 10. So 6 looks like this. And 10 looks like this. So, where am I going to start with 6? We know which one is, like, there's not really a question of, like, what we're going to be using the power rule on. But how am I going to approach having a fraction? Yes, I'm going to bring down that. So we have y prime, which is equal to 4/3 x. And then what is my x to the power of? 1/3, exactly. X to the power of 1/3. And the way that I kind of do that is I just write, like, when I'm like thinking about it, I'm like, okay, so instead of doing -1, I'll just do -3/3. So I don't really lose track. You'll see that especially next week, I have a tendency to write everything down when I'm solving these problems, because I get lost very, very easily. So yeah. All right, what about this one? How do we approach having a variable with power in the denominator? Divide it through, what do you mean? Yeah, I go usually with rewrite. I rewrite it in a form that I'm more familiar with and more capable of working with. So I'm going to call 1 over x to the 4, x to the -4. Exactly. So now that I have it written as x to the -4, we can use our regular rule, the power rule, to bring -4 down. And what is going to be up here? -5, exactly. All right, so excellent job, guys. Let's do a couple more. Let's do 16, which looks like this. And then let's also do 28, which looks like this. Oh, looking at 26. So this is 3t squared plus 12 over the square root of t minus 1 over t squared. Okay, so let's start with 16. I'm going to be using the power rule, and I'm going to be using it a lot, basically. Kind of how I'm going to do this is, if you remember from the beginning of this section, should have been at the beginning of the section, sum and difference rules. Yep. Basically, the derivative of this whole thing together is the derivative of each of these individually, either added or subtracted. So I'm going to first find the derivative for 4.2q squared, which is going to be 4.2 times 2q to the 1. And then I'm going to do minus 0.5q, which if we have q to the 1, we know that it's just going to be 0.5 because we're basically out of q's. And then this, the derivative of a constant, is going to be 0. So I will write this a little bit clearer. This will be 8.4 q minus 0.5. And that's what y prime is equal to. So they can give you a really long chain of all of these things added and subtracted together, but really you just have to do them each individually and then add them all up at the end. Okay, what about this one? Same principle here, but now we have a little bit more finagling to do. We have to rewrite this in a way that's more convenient for taking a derivative. So I'm going to say this is 3t squared. That's fine. How am I going to rewrite this term? What is this going to look like? I know I have my 12. Very close. We have in the chat box 12t to the 1/2. It's actually 12t to the negative 1/2. Yep, exactly. Because our t is going to be underneath here. And just to write it out explicitly, the square root of t is going to be equal to t to the 1/2. So that's the rule that we use to get square root of t here to t to the negative 1/2 here. Okay, and then this one we just covered in number 10. We're going to turn this into minus t to the negative 2. Okay, so y prime is going to be the derivative of 3t squared, which is going to be 6t plus the derivative of 12t to the negative 1/2, which is going to end up being, I'm going to write this out a little more explicitly so that we can follow it algebraically. Minus negative 2t to the negative 3. So let's rewrite it again. All right, there we go. Any questions about how that happened? All right, awesome. That's what I like to hear. So let's also do let's do 46. So I'm still on page 143 right now. I'm going to be doing 46, not 4.6, 46. So the number n of Akers Harvard, the number n of acres of harvested land in a region is given by the equation n is equal to f of t is equal to 120 square root t. Where t is the number of years since farming began in the region, find f of 9, f prime of 9, and the relative rate of change f prime over f at t equals 9. Interpret your answers in terms of harvested land. Okay, so let's start with the first part of this. We're asked to find f of 9. To find f of 9, all we're going to do is put t is 9. So we're finding f of 9 is equal to 120 times the square root of 9, which is 120 times 3, which is 360. All right. Now we have to find f prime of 9. How do we do that? Well, we're not going to be using what we got for this answer. We're going to be going back to the original equation so that we can find the equation for f prime of t. So if f of t is equal to 120 square root t, what is f prime of t? (60 t to the negative 1/2). Good. All right. So now we have an equation. We can use this to find f prime of 9, which is going to be f prime of 9 is equal to 60. And I'm just going to rewrite this as the square over the square root of t. And t is going to be 9. So this is going to be 60 divided by 3, which is 20. So f prime of 9 is equal to 20. Okay, so now we're going to be looking for the relative rate of change, f prime of t, or f prime of 9 rather, over f of 9. So this is just going to be using these two numbers that we just found, 20 over 360. I'm going to kick out the zeros. So this is going to turn into 2 over 36, or what, 1 over 18? Okay. So let's start here at the top. What does this number mean? This 360 in terms of harvested acres is what? It's just going to be the harvested acres. It is the acres of harvested land. Because that's basically the most basic form of this equation. That's what n is equal to. Now we have n prime, or f prime, which is the instantaneous rate of change at f is equal to 9. So what does this mean? Oh, not FT, excuse me. T. In regular language, we're going to be talking about, we're in the 9th year of farming. After 9 years of farming, we've got a rate of change that is still increasing. What's most notable? Oh, we got an answer in the chat box. Yes, exactly. So after the 9th years of farming, we were increasing at a rate of 20 acres per year. So we can basically guess, based on this data, that our 10th year of farming, F of 10, is going to be 360 plus 20, which is going to be 380 acres harvested. So, I'm going to quick finish writing this out. All right. And so this is going to be the relative rate of change. We're looking at how, we're basically comparing how fast it's changing to how much land there is. Or how much land there is being harvested, essentially. So this is kind of a comparison. Okay. Are there any questions about 3.1? Sweet. Let's move on to 3.2 then. So we're doing exponential and logarithmic functions. Yay! We are continuing on learning how to take derivatives of them. And everything that we learned in 3.1 still applies, and there will be some problems that kind of go ahead and use it. So we're going to be on page 148. And we are going to start with, we're going to do problem 2. We're going to do problem 4. And we're going to do problem 8. All right. So let's start with problem 2. We're going to break this down just like we did before. F prime of x is going to equal the derivative of this, and that is going to be added to the derivative of this. So this is what we know, this x squared. So the derivative of x squared is going to be 2x. Showed that in the previous section. What about this derivative, 2e to the x? What is the derivative of that? Well, we know that we have a constant, so that 2 is going to be a constant. So we basically don't have to think about it. We're just going to multiply it in at the end. So I'm going to separate this out, so it's going to be 2 and then e to the x. So what we want to know is, what is the derivative of e to the x? E to the x, exactly. So we take the derivative of e to the x, which is e to the x, and then we multiply it by the constant, because if you remember, we can this is equal to 2 times d dx dx. We pull out that constant, make sure we multiply it back in at the end. So the final answer is going to be 2e to the x. It doesn't change at all. Okay, let's do number 4. Same principle. Five t squared, the derivative of that is going to be 5 times 2, 10 t, plus, just like we did in this last one, we've got 4 as a constant, and e to the t, right like that. Now, what if this wasn't e to the t? What if it was e to the negative t? How would that change what we just did? How would that change your derivative? So just like over here, we're going to separate it out. We're going to say that so our real question becomes, what is the derivative of e to the negative t? Are you suggesting doing something like this? Because that's a very tempting thought based on the power rule. But that's not what we're going to do, because the difference between this and the power rule is going to be that, sorry, my, my mouse is not working very well, and I'm not sure why. That's really weird. Okay. My tablet, whatever this is. Okay. So this is different from the power rule. In the power rule, we have the function like x squared. You were thinking when there was a constant there. Yes. Yes. So I'm going to quick finish this little line here about the difference between the power rule and what we're doing now. Basically, the difference is where the variable is. Here, the variable is in this base area. Here, the variable is up in the exponent. And so it's going to behave a little bit differently, and we can't treat it exactly like we would the power rule because the variable is in the exponent and not down at the bottom. And you'll just kind of see how we do that later on. Yes, we're going to do exactly what you suggested when there is a constant here. We remember our rule e to the kt. When we take the derivative of this, it is k e to the kt. So we're just basically adding that k on the outside, and that is on page 146. And so basically here we're going to consider our k to be -1. That negative sign is k is equal to -1. So the derivative of e to the negative t is going to be negative e to the negative t. So basically how this changes is we have a negative t here, and this is going to turn into a minus sign. Sweet. All right, so what are we going to do about problem 8? There is a rule on page 146 that states the derivative of a, where a is an integer, to the x is equal to ln a times a to the x. Yes. I found this rule to be very stressful because, if you remember back what we were doing with when we had the exponential equations where things were going up by certain percentages and going down by certain percentages, we would have a to the, it was a to the t versus e to the kt. Do you remember this? We had like p, that's not p, p is equal to p naught a to the t type thing. Okay, so do you remember what we would do to go between these two? We would just set them equal. And then we would solve for k. Because we knew that t was going to be a variable in both of them. The only difference is that a is equal to e to the k. So basically how I tend to think of these problems, instead of memorizing this rule, I solve it out every time, which can be mildly time consuming, but it also saves you from memorizing an extra rule. So how I would approach this problem is saying that 2 is equal to e to the k, and I'm trying to figure out what k is. So to do that, I'm going to take the natural log of both sides, right? So now I end up with ln 2 is equal to ln e to the k, and because I have a exponent in a logarithm, I can go ahead and move that outside. So this is going to be k ln e, and the natural log of e is going to be 1, so this is going to be k. So I know that k is equal to ln 2. So instead of thinking about it using this rule from page 146, I have a tendency to say that f of x is actually equal to e to the natural log of 2 times x plus 2e, and then I'm going to have to go through this whole kind of shindig again, where I show that 3 is equal to e to the k, natural log of both sides. So ln 3 is equal to k ln e, which is just equal to k. So k is equal to ln 3 times x. And then I can just use the rules that I learned for the e function. So f prime of x is going to be equal to ln 2 e to the ln 2x times x. Another way that you can write this is just x ln 2, which makes it explicit that the x is not a part of that natural log, plus 2 natural log 3 e to the x ln 3. And I could go ahead and rewrite this so that I have just these like a to the x's again. I can just say that this would be ln 2 times 2 to the x plus 2 ln 3 times 3 to the x. But because I prefer to work in e, because e is a lot easier to work with than all of this other random stuff, I usually leave my answer like this. Does that all make sense? My goal is to take you from a somewhat to a yes. What about this makes less sense than the rest of it? Like, where is the problem here? Do you want me to redo this problem in and break it down even further? Okay. Let's do that. So the problem that we were working on is we've got two of these integer to the x experiences going on here. We have this 2 to the x plus 2 times this 3 to the x. And if you remember, when we had, I always write R when I mean to write P. I don't know why I do it. It's just like I'm just like in the groove, and I'm just gonna draw this extra line for the heck of it. I don't know why. Okay, so we had these equations, right? Where we would have this initial population, we would have this changing in population, and we would be forced on occasion to go between these two equations because sometimes these equations would tell us different things. Like in A, we were working with like explicitly like the percent, like is this rising by 8%? Is it falling by 8%? And with E is just nice to mathematicians. Mathematicians really like E. So it gives us this nice K value. We can take some nice derivatives with it pretty easily, that sort of thing. So E is easy to work with. As you saw in this section, E, like the derivative of E to the X is just E to the X. So it's handy to have things in terms of E. I also don't like memorizing a lot of rules, so that's the reason I kind of go through all of this. When we had P naught is equal to A to the T is equal to P naught E to the KT, one thing that we did was we explicitly stated that these two were equal, right? Because they were both equal to P. And then we said we need to find some way to convert between them. So we divided both of them by P naught, so we got them out of the way. And we ended up with A to the T is equal to E to the KT. And then we said that I don't like need this T here right now. I know that that T is there in both times. So this is going to be the quantity A to the T is equal to the quantity E to the K, quantity E to the K, again to the T. And by my rules of exponents, because I'll be multiplying it through. So, separated this out. Based on this statement, I know that A is equal to E to the K. Correct? So, I'm going to use that same sort of logic. I know I walked down through all of this with my population example, and that's not where we're at right now, but that's just kind of something I wanted to call back to. If I have an equation A to the T, there is a counterpart of that equation where I have it in terms of E, and that is going to be E to the K something. So the reason I'm doing this all is to get this in with a base of E, and I'm going to follow that same exact process. So if I have 2 to the X, I'm not taking any derivatives right now. I'm just going to try to show that 2 to the X is equal to E to the K X, right? So that's where I am right here. So what that means is that, yeah, if this is true, then this is also true. So it's going to be 2 is equal to E to the K. And then I can follow through with my natural logs. Because this is equal to 1. So I end up with k is equal to the natural log of 2. So I'm just going to go ahead and rewrite it up here. I'm going to put the x on this other side just to explicitly show that it's not inside that natural log. And then I'm going to do pretty much the exact same thing. And you'll see a pattern developing where I have 3 is equal to e to the k. And then I've got the natural log of 3 is equal to natural log of e to the k, k, ln e, k. So k here is equal to the natural log of 3. So this is going to be plus 2 times e natural log of 3. And you guys know how to take this derivative, because this natural log is, like, if I have the natural log of a number, it's just going to be like a number. It's going to be a number with a lot of decimal points, but it's just a number. So I can use that natural log to represent that. Yeah, of course. All right. So let's then do problem. Let's do Let's do 24. Okay, so we've got this function, which is r of q, and we've got 3 to the ln q. Excuse me. How am I going to take this derivative? First off, I know 3 is a constant, so really what I need to know is how do I take the derivative of the natural log of q? This is one of those rules that you guys just have to memorize. But if you do enough practice problems, it'll become pretty second nature. So the derivative of the natural log of x is equal to 1 over x. So just like that, what this is going to be, r prime is equal to exactly 3 times 1 over q, or 3 over q. Okie dokies. Sweet. Let's do, well, if you guys, do you guys have any questions about the what's going on here in 3.2? Your exponential and logarithmic rules. This week is really just a bunch of rules. Next week we get into a little bit more like what's going on here. But yeah, this week is a lot of just kind of rules. So let's move on to 3.5. They introduced this here just like with the rest of the rules that they give you, with the purpose of just familiarizing you with the derivatives of the whatever the word is, periodic functions. Ugh, the word periodic just completely left my mind. Okay, so we're on page 164. And we are going to do problem 2. Problem 4. And we are going to do problems Can we do problem 8? Yes, we can. We're going to do 8. Okay. So, problem 2. We've got ourselves a constant and sine x. What we really need to know is the derivative of sine x. So y prime is going to be equal to the constant times that derivative. Based on our rules given to us on page, in this case, it is the bottom of page 162. The derivative of sine x is going to be cos x. So this derivative is 5 cos x. Number 4. I've got the derivative of t squared, which is just going to be 2t, plus 5 times the derivative of cos t. What is the derivative of the cosine of t? Negative sine t, exactly. So I jumped the gun by writing that plus sign. Needs to be a minus sign, minus 5 sine t. Okay, awesome. Now what about number 8? The big thing going on in number 8 is that I have this 3 on the inside. So, basically the best way to remember this by, or at least the way that I kind of think about it, is that it's comparable to e to the kt, in that whenever you take a derivative, whenever you find f prime of x, you're going to take that k outside. And then I need to add the actual derivative of that. So it's going to be cos. And you're also going to leave it up there. So in the same sort of manner as e to the kx, we're going to take out that 3, take the derivative of the sine function, and then also leave the 3 inside. And the reason that when we do that with e to the kx, we do that same thing, k outside, derivative of e to the x, which is the same thing, and the k remains on the inside. So we're just switching it up a little here with the periodic functions, but it's the same type of principle. You'll learn the explicit version of that next week. What this is explicitly is the chain rule, but we don't have to walk through that all right now. This is just the rule that they gave you. So, are there any questions about what went down with these? Sweet. Let's also do, sorry, I'm looking through these problems, trying to find ones that don't involve rules from next week, because this is 3.5, so there's a couple of sections in between us right now. We can do problem 14 though. So problem 14 looks like this. Z is equal to cos 4 theta. All right. Z prime is equal to, what is Z prime equal to? close. Very close. The only thing you have is an extra theta. This is actually going to be, you're right with the negative, -4 sine 4 theta. When I pull this out, I'm only taking out 4, not the variable. Yep. So just like when we had y is equal to e to the 4x, y prime is going to be equal to 4e to the 4x, right? Not 4xe to the 4x. You got it, yep. So it's that same kind of idea. I'm only pulling out that one number. This is going to make a lot more sense, like what this is doing next week when we talk about the chain rule. But for now, this is just how they want you to do it. Think about it in terms of just taking out the one number. Okie dokies. We can also do number 28. Well, that doesn't look to at all. So the depth of the water Y in meters in the Bay of Fundy, Canada, is given as a function of time t in hours after midnight by the function y is equal to 10 plus 7.5 cos 0.507 t. So we've got some very beautiful numbers in here. So the question is, how quickly is the tide rising or falling in meters per hour at each of the following times? We're only going to do part A because it's the same principle for all of them. We have 6 a.m. in part A. So what does T equal? 6, yep, because we're 6 hours after midnight. So I'm going to kind of rewrite the equation. So this is going to be, we're not going to rewrite the equation. If I were to find y of 6 right now, what would I get in terms of like, you don't need to like solve for a number, but like what in principle am I going to be achieving? This, like, in essence, is just going to be the depth of water at 6 a.m. This does not answer the question, which is how quickly is it rising or falling? So in order to find a rate of change, I'm going to need to take a derivative. Let's do it like this. Y prime is equal to, so the derivative of 10 is going to be 0, plus, I've got a constant, so 7.5. And now I need to take the derivative of the cosine of 0.507 t. So what is that going to look like? Well, I've got this junk here in the middle that is just one number, so that's going to be my k. So I'm going to bring that outside. Yes, exactly. I'm going to turn this into a negative sign. I'm going to bring it outside. And it's going to be sine of 0.507 t. So I am going to pull out my calculator. Maybe my phone isn't stressing out. What should I be doing? 7.5 times 0.507. So this is going to be, that's not a 0, this is going to be 3.8025 negative 3.8025 sine 0.507t. Now we have this derivative. We know that for part A, our time is equal to 6. So we're finding this when t is equal to 6. So I'm going to go ahead and punch that into my calculator. And what I ended up with was negative 0.2018. So I know, number one, important information, the tide is falling. And I know that it's falling at a rate of 0.2018 meters per hour. Cool. Application. Any questions about that? Sweet. That's basically all I have for you today. So if you guys don't have any questions, then I'm out of stuff to talk about. Thank you guys for coming so much. If you have any questions during the week, of course, feel free to like email me or something and I'll be sure to talk about it. Yeah. You all have a great night.